All right. And this begins EE 555 discussion on Wednesday, February 12th, 2014.
Okay, good morning, everybody. Today we will see two problems, max mean and weighted fair queuing. And let's start max mean fair cell algorithm with weights, basically. We show the simple version. We'll see the version using weight. All right, so what have we seen so far? All right, can you see? Yes. So fair cell allocation algorithm so far, from what we know, the resources are allocated in order of demand. No source gets a resource share larger than its demand, and sources with unsatisfied demand equal share of the resources, right, of the resource. What we will see now will extend this logic and will support weights, and this means that each queue can have its own weight, and we allocate the resources proportional to the weights. That's the basic. So with that said, what do? The resources are allocated in order of normalized by the weight, which means the more the weight, the more the resource we allocate in its time. No source gets a resource share larger than its demand, obviously, same as previously, and sources with unsatisfied resource shares in proportion to their weights, which means how we distribute what is left, right? We distribute what is left in a proportional to the weights, same thing. All right, so example, compute the max mean fair allocation for a set of 4 sources with demands 4, 2, 10, and weights 2.5, 4, 0.5, and 1. The resource has a capacity of 16. So let's start writing things down. First of all, what we do in such a case, when we have weights, the first thing we need to do is to normalize the weights and make it be equal to 1, such that we can calculate easily the so first thing is, let's say, I'm going to put 2, 3, and 4. The demand is demands over here. We have demand 4, 2, 10, and 4, and the weights WI is equal to 5, 4, 0.5, and 1. And this we will map it to the smallest should become 1, right? That's the first thing we said we'll do. So this is obviously, and we do the same for every other weight. So this will become 2, this will become 8, and this will become, okay? So the logic now is to consist of 16 sources instead of 4. Okay, and we try basically theoretically 1 to each, but of course one resource to each one of the sources, but multiple to each one of the 4, right? Depending on the weights. Is that clear? So what we know is let me write another table that I'm gonna, I will call iteration. I'll give you a wording description of the solution, but I think it's more easy. Here we have 1, 2, 3, and 4. We have over here total, let's say, I'm going to write it like this, 2, 10, and 4. This is the total demand. Okay, so what do we do at the beginning? We divide, as we said, the resources by 16. We have 16, theoretically 16 sources, and we say, divided by 16 equals 1. So I'm going to allocate the weight of times 1 to each source. Do you agree with that? So iteration 1, what I do is over here, what is this? The weight is 5. So I'm going to allocate 5 to the first source, 8 to the 1 to the third, and 2 to the fourth. Okay? Now let's see if we comply with we said that this guy wants only 4. So we have an addition of 1 given. And over here we have an addition of 6 given. So additional resources, we have 7 at the beginning. This guy wants 10 and the last guy wants 4, so we're good. Is it clear so far? Huh? 7 is 1 from here. This, we want 4, we give 5 per 8, right? So we have 1 extra. And for the second source, we want 2 with of the weight. Okay, so we need to redistribute this extra, this additional, that's the purpose of that. So I'm writing down here how much is the extra, and I'm going to redistribute proportionally to the guys that want more resources in the next iteration. Make sense? So, how much does this guy want? This guy wants 4. How much does this guy want? 2. And how about those 2 guys? This guy has 1, and this, so far he has 2. And what are their weights? Their weights are 1 and 2, okay? So I'm going to redistribute the 7 resources that I have proportionally. Make sense? But now the weights are not going to be, I'm not taking into account the total, which is 16. Now my total is 3. And I know that this guy 1 over 3 and this guy 2 over 3. So I'm going to redistribute proportionally, which means that this guy will get 1, what he has 1 already, plus 7 divided by 3. And the fourth guy will get plus 2 times 7 divided by 3. Okay, so let's count now if we are exceeding the, all right? So the last guy wants a total of 4, and we gave him more than 4. How much more? Actually, we gave 4 divided by 3, but he wants 6. 6 divided by 3. 6 divided by 3, which is 2. Make sense? So we exceeded by how much? 8 by 13, right? Okay, what we need to redistribute in the next round. Make sense? So round iteration number 3, or whatever you want to call it, we keep our first two sources because they are okay. And what about the next guy? The next guy will keep whatever he wants, and which is 4, because we gave him more, and the rest is going to be to the guy that is left, only 1. And how much is left? It's 1 plus, sorry, it's 8 by 3 plus, sorry. I'm very right, sorry. Thanks for that. 8 by 3, yes. I confused the line for the ratio. Okay, so 8 by 3 over here, and we'll give that to the last guy, right? So we 7 by 3 plus 8 by 3 equals 5. So it's 1 plus 5 equals 6. We don't have more resources. And that's the end. Does that make sense? So you might want to avoid this table over here, although I try to put it this way just for but you know, you can do the calculations in your mind, and I do first and then I redistribute and so on and so forth. Any questions? Guys? Okay. So that's the first example over here. So final, the shares, 4,2, 6,4, which is the mean weighted algorithm. Allocation anyway. All right. That was okay. Let's see another problem now. So now we'll see weighted fair queuing problem. This material over here. All right. Okay, I found it. We have seen this setting many times so far. We have 3 flows, 3 groups, and the following arrival process. Supposed to receive 1/6 of the channel. Group 2 is supposed to receive 1/3, and group 3 1/2 of the channel. All right? They are clear here, but this is time. Number, plus, all right? So all the examples are based on that, such that, okay? So the same holds here. We have the first packet arriving at 1 of length 1, the second packet of the same queue arrives at 1.5, then from the second queue arrives at 1.7, the second packet from the second queue at 2.3, and so on and so forth. We have another for the first, which is Q3, all right, at 3.5. Okay, so what we want to calculate the weighted fair queuing allocation here, all right? What have you seen in the class so far for that? We have seen fair queuing, right? So in the weighted fair, the same concept, meaning we do all the calculations in the GPS. We find the order and then we do the allocation in the weighted fair queuing domain. Same thing as. All right, so with that said, let's write down what equation. Let me get something. What do we know? We know that the starting tag, as we say, is equal to the maximum, the finish time for Qi, k minus 1 is the packet k minus 1, and at time t, comma rt, which is the round. And also we know that fi, comma k, comma t to s, I, comma k, comma t, where s is defined as above. Let me. This is the definition of s, I, comma, and plus the length of the packet, iota, comma k, meaning from q, packet k from qi, or from group I, whatever you want to call it, and divided by the weight that the professor gave for the weighted fair queuing. All right? What else do we know? We know that the slope in this case will be dRT over dt equals to the capacity by the total number of weights. But be careful here, the weights active flows. Okay, so depends how many ready. We don't start at the beginning with, for example, in our example, we don't start at the beginning with all the flows being there, right? Flow 1, then flow 2, then flow 3. So this slope changes over time depending on how many sources we have. That's why the final plot for the RT time is a piecewise linear graph, right? Because we flows, then we split basically our traffic to, our resources, we distribute the resources to more sources. All right, so we know that W1 equals 1 over 6, W2 equals 1 over 3, and W3 equals 1 over 2. Okay, let's see how this graph first of all looks like. Domain. Have you seen this in the lecture notes? What is that over here? This is the GPS, the generalized processor set, the server load over time, okay, for each one queues that we have in the system. And then we have the total. So, again, it's not very... Yes, I wish I had it in PDF and work with that. Can you see it? At least some, like this curve, we want this slope is the UT. This guy is UT. And this guy is... Alright? So what happens over here is that we x-axis, it's the time instances that we have arrival of packets or some other event anyway. Plot in the vertical axis there. Okay? So for the first flow, you have seen these plots again, right? Can you create this plot by yourself? We can go over it, and the main basically this and every other algorithm that we saw so far is that we have weights, which means that whenever allocate the bandwidth in infinitesimal time, as we said, right? We allocate the bandwidth and we allocate it proportionally to the weight. That's the whole story. That's the only thing that changed. At the beginning, we have only one packet from the first queue. length of 1, so the load is 1. This is at time t1. Why we say that? It's given over here, right? t1, length 1. Make sense? So what happens at this time instant? We have another arrival from the same queue, 1.5. Okay, this is 1.5, and then there is at 1.7 an arrival from the same. So we denote it with this lighter line anyway, light color. Okay, the first guy over here, till 1.5 he was by himself, right? So although we have a weighted setting, we don't care over here because he's by himself, so he gets all the resources, right? So the slope over here, we don't talk really about slope, but it's 1. If you rotate, it's not 1 now, but it's -1, right? So this means anyway that we go as fast as we can down, meaning we, with this first queue. All right, perfect. So the time 1.5 we have an arriving, so we add that to the load, and till 1.7 we control. Make sense? All right. So what changes over here? The second guy comes. So at this time instant, how do we distribute we have the first and the second. The first guy gets 1/6, the second gets 1/3, 2. So what is the proportion of weights over here? In this region, from here to we're talking about Q1, right? This is the Q1 and this is Q2. So what is the slope of this guy and it's what? 1/3 and 2/3. Why is that? Because the ratio of the two, we just, look what is the proportion. So this one guy is twice bigger than the other. Okay, so that's how we distribute the load. So continue for the first guy till the time that he has the second arrival, and then we go up by the same slope until we have another flow. Make sense? Okay, so it's stable till here, till time 3.5. Why 3.5? Because we have P31 arriving, a new flow in the system. So in this type of problems, whenever we have a new, the slope changes. Not a new packet can wait. A new flow changes the slope. So from here and at the end, we use the same logic, right? Over here we have the other flow that arrived at 3.5 is here, not here. At 3.5 we have the third flow, which changes again the slopes. How? Now we have the proportions that we had initially. 1/3, 1/2. Half. Over here. Do you agree? Why this is half? Let's see half. This is 3.5 and it goes up to 5.5. Why it goes to 5.5? Because he has, very good, he wants to send a packet of 1, and the resources he gets is, and we have total capacity of 1, right? So he needs double the size of the packet to send. If we start at 3.5, he will transmit it by 5.5. Make sense? This is flow. Okay. And remember, we are using GPS. The minute he comes in, starts, getting resources. All right? Okay. So, same applies. What we need to be careful over here, what happens when people leave from the system. For example, at this time instant, so we change the slopes again, and we go back to the two slopes, 1 and 2/3, right? And then we go back to the, so we have a small piece over here with these two slopes, and then we in the last part. Is that clear? Okay, so that's the GPC diagram. Why we need this diagram? We're doing weighted fair queuing, right? So we need this because we will use this point to infer what's going to happen to our diagram. Also can create, you'll see that in class most likely, we can create this table, which is a GPS table detail, what happens every time instant. Okay, we won't see this, another more enhanced table, which is related to us. Okay, so so in our diagram, we expect that we have a change in the slope of RT. What is RT? The round number, right? What do we want to plot? I didn't tell you. I forgot to tell you. We want to plot as the professor gave an example yesterday. I don't know if you saw the example. Did you see it? Posted on DEN. So if you download the lecture slides for yesterday's lecture, at the end he has a complete example on fair queuing. Please take a look on that, because this is a simple here. Okay? So what the professor posted is the diagram of the round number for his example, which is weights. Weights equals to 1. In our example, we'll see why the graph looks like this. Fair queuing, the round number versus time for our weighted fair queuing example. We're going here. I want to tell you why we have these change points and our graph looks like this. Okay? So first, write down some things that we saw or some things that we... All right, so arrival times or departure times that can affect how many flows we have in the system. At the beginning, we have arrival at time 1, another arrival at 1.5, another arrival at 1. Another arrival at 2.3, at 3.2, 3 pretty accurate the scale, but I guess we are fine with that. Another over here, which is 5.5, and then we'll see what else we have together. So from time 1 to time, we have how many flows? One to 1.7. We have one flow. Show you the over here. Till 1.7, we have 1.7 is when the second flow arrives. So over here we have one flow. Okay, from 1.7 to a time to 3.5 is when third flow arrives. So we have two flows over here. And from here, 3 flows till 5.5. And then we have, as we saw, from 5.5 to 5.7, do the calculations. We have the complete derivation. If you want, you can verify it at home, okay? Over here, it's 7. And this is... this guy really, we care about the change of slope, which is at 5.7, and then we terminate it at 7. Okay, from 5.5 to 5.7 we have flows, and then from here one flow till 7. So we will use this fact in order to draw the graph, okay, because it's very important for the slopes that we need to know. Now we have this, let's go and calculate the change points where the slope changes. First of all, this happens at time 1. We have that dRT over dt is equal to what? 1 over 1 over 6. This is the weight of the active flow. Remember, at time 1 we have only one flow with weight 1 over 6. So we apply the equation, the slope is given by this, the rate of change. Okay? So the first slope will be 6. What happens to the first finish time? 1 comma t will be what? The maximum, this guy that is not defined is 0, comma, how much is this? Zero at the beginning, right? Have 0 plus 1, what is that? Is 1 over 1 over 6. 1 over 1 over 6, 6. Alright? Okay, so at t7, the other change point over here, with now what we are finding is the slope, right? That's what we need in order to draw the graph. How much is the weight now? Or in other words, what is dRt over dt? Capacity 1 over what? Half. Very good. It's 1 over 6 plus 1 over 3. Gives what? This gives 2. Okay? Can we find the F? Any? This can be done from the graph more easily, right? We can apply the equation that we don't have yet. What we need is how we define RT. Right? Sorry. Over here, I didn't give you the equation for RT. So that's the only thing we need, because we have the weights, we have the length recursively, and then we need RT to find if we want FIs. Okay, we'll go to that. And what's the last change point is at 3.5. 3.5, where the weights now are, let me write this, why we use those two guys. So now the weights are 1 over 6, W2 1 over 3, and W3 1 over 2. So dRt over dt equals to 1 over equals 1. Any questions so far? Okay, so that's a different slope than the slope we saw previously. It was the utilization curve, the server load. All right, so let's see. Now let's go back to this graph. So the part, the first range will be from 1 to 1.7. Do you agree? Okay. Whenever this is 1.7, what is the slope of this piece? It's 6. What does this mean? How do we calculate the slope? This means that y1 minus y0 over x1 minus x0 equals 6. Y minus 0 over 1.7 is equal to 6, which gives that y equals 4.2. Make sense? That's this data point over here. The round time, the round number at, make sense? Okay, the same logic applies for all the data points slope. We find the y coordinate. Okay? All right, so we need here, what we need is do the same for all the change points. And for that, it's not very obvious change over here, right? You need to do something like that. I have a departure here in my GPS algorithm. So I share now the resources with two flows back and then with one. That changes. You might say, oh, okay, I'm sharing by 3 everything till here. And you might be finishing slower, but it's not the case. All right. So what else do we have? Do the same for all the points in the y-axis. And now let's at t equals 1.7. I hope you understand this, right? We are missing also is if we want to find the RT, here we can find all the RTs, but if we want to see the equation of RT, what is the equation of RT? And by the way, the RT, you might see it represented as VT, and VT time. So when they proposed this algorithm, they did a mapping a real-time axis to the virtual time, which means in the GPS algorithm, when things, not the GPS, really, let me think, is the GPS? It's not the GPS. No, it's this virtual time, basically time axis. Okay, and we create, depending on how many flows are sharing, we extend the virtual axis and we map it to a different data point. This is the RT basically. Also, you can see it as VT. I have a table to show. It's nice. Over here. Okay. This is the evolution of the weighted fair queuing algorithm. Please go and verify this home, like all the points. We'll see what each one of these things means. And so basically, in the time as we know, in the GPS, right? Diagram that we drew previously, we have the load. We know what this is. What is dt? Is what? The virtual time I told you, right? It's basically RT for us. Value of RT here. We found previously this data point, 4.2. We can find this data point, 7.8. With this data point and this data point. Those are the data points where we have a change. Okay? What else the table has? Same thing, the group number, the packet number, the size, the start and the finish, and how many packets in each of the queues we have. We measure the delay and we get the average. Make sense? Okay, so one can use over here too is if you want analytically to find the RTs and not graphically, what we can do is we can use this equation. Thank you. To find RT, we can also use this equation, VT1, let's say, plus some time interval, x, is equal to VT j minus 1 plus over summation of WI, active flows. Active flow weights. Does this make sense? This is just find the VT, I'll call it from the graph. Anything more than it's basically the slope, okay? So if you apply this equation, what we can get, for example, is at t equals 1.7, we have Vt equals 0.7 over x. Everything else is 0, and this gives 4.2. Or at t equals 2, we can have Vt equals what? 2, which is the previous time, 4.2 plus. What is at t equals 2? How much is after? Here it was at t equals 7, by 1.7. This guy is 0.3 units far from the previous, so we have x equals 2.3. 0.3 over 1 over 6 plus 1 over 3 is equal 4.8. So you can apply the same table over here and verify how we get those VT values. For each t, you get this. Make sense? And then you plug it into the formula for a final phase. Is that clear? So now we have all the pieces to solve the puzzle. It's not easy, it's very, it's kind of quite involved. Do you have questions on that? Guys? I know it's boring, I know it's kind of fuzzy. I guess tomorrow we'll profit this. Hopefully better than me. Okay, so if you don't have questions, we can close here and we can talk after the discussion. Thank you.
Concludes EE 555 discussion on Wednesday, February 12th, 2014.